The filthy rich and the pure mathematicians typically don't see eye to eye. However, if you ask either one, they'll readily tell you that equality is evil. What does the modern mathematician mean when they say equality obstructs richness? Well, in a sense, this is a categorification of a more concrete claim. Uniqueness is boring. Of course, these so-called propositions are utterly meaningless when presented this way. The decategorified proposition is a dejargonification of the more precise statement that the theory of zero groupoids is a strict but conservative extension of the theory of negative one groupoids. The original proposition is analogously referring to the statement that the theory of one groupoids is a strict but conservative extension of the theory of zero groupoids. If you've watched my previous video on equality, you may have seen these words before. While the exposure therapy might help you with what's to come, the video doesn't actually define what groupoids of any dimension are. Rather, I just explain how such groupoids feel. To recap, in case you hate supporting the channel by watching my other content, a negative one groupoid is a universe wherein everything is the same. In theory, this is enough to go inductively and define n groupoids for every finite n. However, this might be too degenerate of an example for this to be informative, so let's work up another couple of dimensions. A zero groupoid is a universe where, for any two objects x and y, there is a predicate x equals y representing whether or not x and y are equal. For context, most of classical mathematics happens within a zero groupoid. We hit the 20th century by categorifying one more time. A one groupoid is a universe where, between any two objects x and y, there is a collection of isomorphisms, which can be thought of as certificates or proofs that x and y are the same. Intuitively, having distinct isomorphisms between x and y reflect that these objects carry non-trivial self-symmetries. After all, symmetries are an expression of an object being equal to itself in a potentially interesting way. In general, we can understand n-groupoids intuitively by induction. An n+1 groupoid is a universe where, between any two objects x and y, we have an n-groupoid of equivalences. Increasing groupoid dimension endows objects with an increasingly rich notion of symmetry, since these symmetries will themselves carry non-trivial self-symmetries of their own. Picture, for instance, a space where all of its points have infinitesimal symmetries or dimensions packed into them. While induction allows us to produce a theory of n-groupoids for larger and larger n, we can actually use this schema in reverse to decategorify as far down as we want to go too. It's not that interesting though. You can argue that n-groupoids are trivial for all n strictly less than -1. When n is greater than or equal to -1, the theory of n+1 groupoids is always a strict but conservative extension of the theory of n-groupoids. This provides us with a tower of strict inclusions, which makes you wonder, can we take this construction to infinity and conceptualize a theory of infinity groupoids that subsumes all of these finite dimensional theories? The equivalences between any two objects x and y in a putative infinity groupoid should themselves form an infinity groupoid, implying that a theory of infinity groupoids would be an end to this categorification story, a fixed point, if you will. So, what is an infinity groupoid? Well, if you want a serious answer to this question, I'll have to stop putting off defining groupoids in smaller dimensions. There really isn't much to say about negative dimensional groupoids. They're probably more a basis for arguments about ontology or something. I don't know. Of all the things I'm unqualified to talk about, philosophy is something I'm unqualified to talk about the most. But anyway, if all objects of a negative one groupoid are the same, then the only interesting thing we can say about a negative one groupoid is whether or not it has any objects at all. That is, whether it is non-empty. In this way, negative one groupoids correspond to truth values. If you're wondering why there are ellipses here, you must be new to the channel. Welcome to my little corner of the internet. Please enjoy your stay here. Per the guidelines, this community is very inclusive. Accordingly, to ensure everyone has a good time, I do ask you to do some introspection, because you just assumed the law of the excluded middle. Hell no, to the no, 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 hell to the no. Let's start for real with the first actually interesting dimension, zero groupoids. Besides the ontological question of what is an object that persists from lower dimensional groupoids, our first taste of mathematical substance is in the predicate equality. I appealed to your intuition to skim over this word, but if you watched my video on intuition and didn't get caught up in Dunning-Kruger, you know that your intuition cannot be trusted. So what exactly do I mean by equality here then? Well, at the very least, equality is a binary predicate on the objects, which means it's a kind of map from pairs of objects to a truth value, or a -1 groupoid. In order for this predicate to deserve the name equality, it had better feel like equality. This means a few things to me. First, it means that any object x had better be equal to itself. In other words, this predicate should be reflexive. If ever x equals y, we should definitely hope that y equals x as well. This is to say that equality is symmetric. Finally, in order to be able to chain equalities together, whenever x equals y and y equals z, we should expect that x equals z. This is to say that equality is transitive. Altogether, we have a definition of zero groupoids. It's useful at this point to talk about a few other things. For example, how do we map between or compare zero groupoids? This is achieved through zero functors. If you think of zero groupoids as sets, then zero functors are just functions. Specifically, they send objects of one zero groupoid to another in a way that is well defined, in the sense that equal objects of x get sent to equal objects of y. We should probably also say something about how zero groupoids are an extension of -1 groupoids. Remember that all objects of a -1 groupoid are equal. In other words, the -1 groupoids are precisely those zero groupoids for which the equality predicate is always true. There's one last thing I should say before moving on. There is a way of going back from zero groupoids to -1 groupoids as well. In fancy jargon, this inclusion of -1 groupoids into zero groupoids admits a right adjoint, which I could call pi-1. Explicitly, pi-1 takes a zero groupoid and then replaces its equality predicate with the one that is always true. More intuitively, it sends a zero groupoid x to the truth value corresponding to the predicate is x non-empty. Pi-1 may not appear super interesting at this dimension, but it's a surprise tool which will come in handy later. Alright, let's hop up a dimension and define one groupoids. Once again, I'm going to look over the fact that I haven't defined what a collection of objects is. The key structure of a one groupoid is a map from pairs of objects x and y to a zero groupoid of so-called isomorphisms from x to y. I've motivated why this is useful in my earlier video on equality, but just so that we can have something concrete to think about, let's think about enhancing the zero groupoid of natural numbers. The natural numbers serve to classify finite collections of things by their size. We can therefore use the zero groupoid of natural numbers to express, for example, that the number of subfields of Q adjoin a primitive cube root of unity and a cube root of 2 is the same as the number of subgroups of the symmetric group on 3 elements. However, this statement on its own is not terribly useful, even if you know what that statement means. What would be more useful would be a demonstration of this fact. Two sets have the same size if there is a one-to-one correspondence between their elements, so it would be better if we actually had such a correspondence in this case. Having such a correspondence proves the earlier equality, but this is more explicit and therefore more useful. This is an example of an isomorphism. In order to make this new concept of an isomorphism precise in general, we need additional structure. For example, the fact that any object x is equal to itself should be self-evident. We express this by requiring for every object that there exists a special isomorphism to itself, which we call the identity isomorphism. On finite sets, the identity isomorphism would correspond to the one-to-one mapping that's obtained by doing nothing to each element. Reflecting the symmetric nature of equality, if I have a proof that x equals y, I should hope to be able to reverse this proof to create a proof that also y equals x. We can express this with a zero functor from the isomorphisms from x to y to the isomorphisms from y to x, sending any isomorphism to its so-called inverse. For example, over finite sets, an inverse isomorphism is just the one-to-one correspondence going in the opposite direction. Why should inversion be a zero functor? This is because an isomorphism should completely determine its own inverse. If I have two isomorphisms f and g that prove that x equals y, and these isomorphisms are actually equal to each other, then the isomorphisms f inverse and g inverse should also be equal. Finally, we should expect that proofs can be composed together. If I have a proof that x is equal to y and a separate proof that y is equal to z, then I should be able to combine these proofs to prove that x is equal to z as well. On finite sets, this composition of proofs corresponds to composing one-to-one correspondences as functions. In general, we can express this transitivity with a zero functor from composable pairs of isomorphisms to their composites. With all that new data, we can express that isomorphisms reflect equality, but there's nothing here to reinforce the intuition that composition or inversion of isomorphisms behaves as we would expect. For example, suppose that you have a proof f that x is equal to y. Then you can use this to create a new proof that x is equal to y. What you do is you first take the identity proof that x is equal to x, and then you compose that with your proof that x is equal to y. Et voila, a brand new proof that x equals y. Of course, given that we expect that the identity proof doesn't actually do anything, this composed proof should not really be new from the original f. To enforce this, we leverage the equality predicate on the zero-groupoid of isomorphisms, saying that the composite of an isomorphism with an identity on either side is equal to the original isomorphism. Now, suppose I have proofs that x equals y equals z, and z equals w. Then I should expect from transitivity that x equals w, and this can be proven by composing the three proofs I already have. However, there are technically two ways to combine these proofs together. On one hand, I can build a proof that x is equal to z, and then use this to build my proof that x equals w. Or I can start by building a proof that y equals w, and then use this to build a proof that x equals w. A priori, these are technically different proofs. However, there isn't anything truly distinct about these proofs either. To remedy this, we assert an associativity axiom, which expresses that the order of composition does not affect the resulting isomorphism. Finally, we have an axiom to express that inverting an isomorphism amounts to performing the original isomorphism in reverse. Specifically, if you compose an isomorphism with its inverse, you should expect a proof that is the same as having done nothing. That is, you should recover the identity isomorphism. This completes the definition of a one-groupoid. Now, before we can properly compare one-groupoids with zero-groupoids, I should also say something about how to map between one-groupoids. That is, I should say something about one-functors. Just as a zero-functor is a mapping of objects that respects equality, a one-functor is a mapping of objects that respects the structure on isomorphisms. This means that a one-functor f from g to h sends isomorphisms from x to y in g to isomorphisms from f of x to f of y in h. A one-functor should also preserve the other structure on one-groupoids, namely, preserve the identities, composition, and inverses. Morally, it's clear that the theory of one-groupoids is just an amped-up version of the theory of zero-groupoids, but let's make this a bit more precise. Recall that a zero-groupoid's equality predicate can be thought of as a map from pairs of objects to a negative one-groupoid. Since we know that negative one-groupoids embed into zero-groupoids, we can use this embedding to convert the equality predicate into a zero-groupoid. In other words, if two objects x and y of zero-groupoid are equal, then this embedding provides us with an essentially unique isomorphism between x and y in the corresponding one-groupoid. The uniqueness of these isomorphisms give us very little choice for what the identities, inverses, and compositions ought to be, so altogether this does indeed upgrade our zero-groupoid to a one-groupoid. This uniqueness also ensures that the only one-functors that exist between zero-groupoids are just the zero-functors themselves. This shows us how to embed zero-groupoids into one-groupoids, but this embedding similarly admits a right adjoint, which I could call pi0. The way pi0 works is to apply pi minus 1 on only the isomorphisms. In other words, pi0 is the reduction that forgets the proof of equality. Two objects are equal in pi0 if they had at least one isomorphism between them in the original one-groupoid. For example, pi0 of the one-groupoid of finite sets decategorifies it to the zero-groupoid of natural numbers. Although I have shown you how to categorify from negative one-groupoids to zero-groupoids and then from zero-groupoids to one-groupoids, this categorification procedure is hardly a rote routine. Sure, some steps have clear generalizations, but it seems like every time we move up a dimension, we introduce more data, and then this data is subject to brand new axioms that we didn't even see in lower dimensions. To really appreciate how strange these brand new axioms can look, I think it's worthwhile to walk through another step of categorification and talk about two-groupoids. The most obvious part of this categorification is that a two-groupoid comes with a collection of objects and that there is a mapping from pairs of objects to a one-groupoid of proofs of equality. We could call objects of these one-groupoids two isomorphisms or two equivalences. We can also categorify identity, invertibility, and associativity, the latter two upgrading from zero-functors of zero-groupoids to one-functors of one-groupoids. But what about the unit invertibility and associativity axioms? For example, do we assert that the composite of any 2 isomorphism F with its inverse is equal to the identity 2 isomorphism? No, this wouldn't actually make any sense. Equality only makes sense in a 0-groupoid, but 2 isomorphisms from X to Y form a 1-groupoid. Trying to use equality here is since we have a 1-groupoid instead here, rather than being able to say whether these 2 isomorphisms are equal, we instead require proofs that they are themselves isomorphic. In particular, to express the invertibility axiom, we need to provide an isomorphism between the composite of some F and its inverse with the identity 2 isomorphism. Milking the analogy that isomorphisms serve as certificates of equality, think back to the one-to-one correspondence I ripped from Galois. A priori, it may not be completely obvious that composing these 2 maps amounts to doing exactly nothing, so this fact probably warrants a proof. I mean, I'm not going to provide a proof. We've successfully categorified invertibility, but there should similarly be canonical isomorphisms exhibiting the unit and associativity axioms from 1-groupoids as well. Well, that's all we need for 2-groupoids, at least as far as data is concerned. The secret sauce is that we need these new canonical isomorphisms to align coherently with our expectations of them. The first coherence constraint is quite natural. No, really, it's about naturality. Take inverting, for example. Since sending a 2 isomorphism to its inverse is given as a 1 functor, it also provides a means for horizontally inverting isomorphisms between these 2 isomorphisms. That is, an isomorphism between F and G can be canonically transformed into an isomorphism between F inverse and G inverse. For this mapping to be natural, we should expect that the 2 paths on this square from F inverse composed with F to the identity on X should be exactly equal, and similarly for this other square. The commutativity of these squares is exactly what it means for eta and epsilon to be natural transformations in F. Of course, the same naturality constraint applies to the uniter and associator canonical isomorphisms as well. Are we done? Of course not. Naturality is hardly a coherence constraint. To illustrate my point, suppose we are composing the following 4 2 isomorphisms together to demonstrate that X is the same as V. There are actually 5 ways to use composition to combine these 4 2 isomorphisms together, and the associators tell us that they're all canonically isomorphic to each other. Well, actually, what does it really mean to be canonically isomorphic to each other? Roughly speaking, to be canonical is to say that there is a uniquely obvious isomorphism, but this isn't true without requiring a strong coherence condition on associators. Explicitly, the coherence condition in this case is that the 2 paths on this pentagon compose to equal isomorphisms. It turns out that this constraint on its own is enough to say that any way you combine associators together to reassociate a composition of 2 isomorphisms will be equal. If you've watched one of my previous videos, then this pentagon might look familiar, and boy is it all too familiar to me. Anyway, there are similar coherence diagrams for the other structures, but I'm not even going to bother. Once you throw all of the necessary diagram soup into a bowl, you get a complete definition of a 2-groupoid. Of course, this concept comes with its own flavor of 2 functors and whatnot, but you can consult Johnson Yao for all of that goodness and more. We can also conservatively embed the theory of 1-groupoids as those 2-groupoids whose isomorphisms between 2 isomorphisms are all trivial. Of course, this embedding emits its own right adjoint, which I could call pi1, acting by reducing all isomorphisms between 2 isomorphisms to strict equalities. After my video on Animal Farm, you might have had the impression that going from n-groupoids to infinity groupoids was just a hop, skip, and a jump away. Well, I've hopped, skipped, and jumped over as many details as I felt was reasonable, and we're arguably not even in a good position to talk about 3-groupoids. Nice. What? You still want me to define infinity groupoids? Well, I could just say no. But let me say it in cursive. Let's just make believe that if Ross Street dared me to, I could pull all the necessary coherence diagrams out of my toque to put together a complete definition of n-groupoid for any finite n. Then we're back to where I left you hanging in the last video, an infinite tower of inclusions of n-groupoids into n+1 groupoids. Assuming you've learned your lesson and attended Kant's Academy, you might guess that we can take this to infinity by taking an appropriate colimit. This guess is absolutely correct. However, there is a lot riding on the word appropriate here, and don't forget that we're already suspending a lot of disbelief. First of all, where even are we? You can't talk about colimits without defining the ambient category. I've implied that there's a notion of n functors between n groupoids for every n, so you might have the impression that the n groupoids form a category, and so we're computing a limit in the category of categories. Unfortunately, this is wrong on many levels. First of all, categories don't form a category. If you disagree, that's fine, you're just evil. We don't generally care about isomorphisms of categories, we care about equivalences of categories, and that means that categories instead form a two-category. Secondly, and this is technically an extension of the first point, n groupoids also do not form a category. I'll let you think about it, but n groupoids form an n+1 category for every n. This means that the diagram of inclusions I've written down consists of arbitrarily high-dimensional categories, and so the diagram itself must live in an infinity category. Great. So in order to define infinity groupoids, one must first invent the universe. Okay, maybe you don't need the entire universe, but you still need the infinity one categorical part, which doesn't avoid the circular predicament we're in. For the sake of argument though, let's suppose we hacked together a workaround partial universe in which this diagram makes sense. Then we're still wrong. The naive colimit of this diagram would just be what is effectively the union. In other words, we would just get the collection of finite dimensional groupoids, not infinity groupoids. Luckily for us, the collection of finite dimensional groupoids is categorically very ugly, which is a property that is not shared by the n groupoids for any fixed n. We can therefore fix this issue by restricting our colimit to a subcategory of beautiful infinity one categories, specifically the locally presentable infinity one categories and the left adjoints between them. Ignoring the fact that I haven't defined any of this jargon to you, this gives us a correct formula. Before you get too excited though, we have another problem. Even if you do know what locally presentable infinity one categories are, this colimit is very hard to calculate directly. Luckily, we've all read Chapter 5, Section 5, Subsection 3 of Jacob Lurie's higher topos theory. If you remember from back when we weren't suspending all this disbelief, I mentioned that all of these inclusions of n groupoids into n+1 groupoids admit right adjoints pi n that go in the opposite direction. Well, leaning on corollary 5.5.3.4, we can equivalently compute this colimit of inclusions as a limit of these pi n's. What does this buy us? Well, we can actually compute this limit. Well, insofar as we can compute limits of plain old infinity one categories. But trust me, this is really easy. After sweeping all of these highly non-trivial tasks under the rug, we can finally say something about what an infinity groupoid is. An infinity groupoid G is just a sequence G0, G1, G2 up to infinity where Gn is an n groupoid equipped with a sequence of equivalences from pi n of Gn+1 down to Gn for every n. You can think of each Gn as the n-dimensional approximation or truncation of the original infinity groupoid G. But G, I hear you say. What's the combinatorial definition of an infinity groupoid? If you've written down a combinatorial definition of a 3-groupoid and are still asking this question, you need therapy even more than I do. Mathematicians are enabled to actually study and work with infinity groupoids without drowning in coherators precisely because they can sidestep any algebraic formulation of the theory. This inevitably leads to the question of how this is achieved, but to understand this, we need to grab some duct tape and strap ourselves onto the big one. That's right, ladies, gentlemen, and the classically excluded middle. After all of our waiting, we're finally ready to go to space. Oh well. If you're still here, thank you for watching. If you liked what you watched, you don't need to suspend any disbelief to express that somehow. If you didn't like what you watched, that's fine. No matter how much you feel like I'm just putting arbitrary data out there, there's always one fan keeping me in line and making sure everything I do is homotopically coherent.